Welcome back to Topics in Statics. We're on particle equilibrium in 3 dimensions. Last time we talked about the conditions for equilibrium, which is that the vector sum of the forces is equal to 0. In the case of 3 dimensionals, we break it up into components. We get 3 scalar equations, x, y, and z. Each of those has to be 0. Once again, because I've got 3 equations, at most I can solve for 3 unknowns. If I have more unknowns than that, I either can't solve it or I've got to have something else that gives me a condition to get another equation. The big problem I have with problems in 3D is it's really hard to draw a free body diagram. At least it is for me. In general, I work off the picture that's given with the problem. I try not to write on the picture given by the problem. The reason is the more you write on it, the harder it is to see. And if you have to back up and you need more information, you got to go look at that picture. If you've written all over it, you can't see what's going on anymore. So typically, yes, I kind of draw a free body diagram, but where I really try and be careful is to make a list of the forces on the figure written as Cartesian vectors. I make a list, and then I apply my equation of condition for equilibrium there. And we're going to end up solving 3 simultaneous equations. It's okay, we can do it. It's not that bad. So let's try a problem. So here's our condition. We got this object hanging at A, weighs 300 pounds. Find the tension developed in those other 3 cables. So let's have a plan. What's our plan going to be? What are we going to do? Plan. First, we're going to draw a free body diagram. We're going to do the best we can with that. But by and large, I'm going to work off this picture that's already on the page. Second, and this is the important part, I'm going to write all the forces as Cartesian vectors. I'm going to make a list. That's what I'm going to use once I start applying the equations of equilibrium. So I'm going to apply equations of equilibrium. So that's the plan. That's what we're going to do. So let's start. Let's go to another page. So the first force I'm going to write down is the weight. Right, that weight is that 300 pounds. Which direction does it point? It points in the negative k hat direction. So there's my first force. My next force is going to be TAB. Let's just call it TB. Save ourselves a little bit of headache, fewer subscripts. So TB. Right, it points from A to B. It has a magnitude of TB, and it points purely in the I hat direction. TC. TC is going to be a little bit more trouble. It has a magnitude again of TC. But then I've got to break it up. Right, this is one of those problems where first I break it up into A prime. There's A prime, that red vector I just drew on there. And then I'm going to resolve A prime. So in the Z direction, all I'm going to get is TC times the sine of 60 degrees. And that's in the k hat direction, and it's positive. So that means in the x and y directions, I'm going to get a cosine of 60 degrees. And that's going to get me to that red vector. But now I project over to the x-axis. To project to the x-axis, I'm going to need a sine of 60 degrees. Sorry, 30 degrees. Sine 30 degrees. And I'm going to get a cosine of 30 degrees over here. Now the x component is positive. This is j hat. This is I hat. The x component is negative, so I'm going to put a minus sign in front there. Then we've got the vector TD, which has a magnitude TD. And here they give us direction cosines. Well, not quite. They give us the direction cosine alpha is 120 degrees. So I can write that one in there. I get cosine of 120 degrees I. But now rather than pointing to the positive y-axis, that 60 degrees points to the negative y-axis. Right, so I get a minus sign here. So I get minus cosine 60 degrees j hat, and then plus cosine 45 degrees k hat. Right, if you don't like that cosine 60 degrees, if that's 60 degrees, then to the positive y-axis, I could have written it this way. This is cosine 120 degrees I plus cosine 120 degrees to j plus cosine 45 to k. All of those are degrees. Lift off my degree signs. So I get three equations now. Sum of the forces x equals 0, which gives me TB minus, and I can calculate that. That's 0.25 times TC minus 0.5 TD. I get the sum of the forces y equals 0. I get 0.433 TC minus 0.5 PD, and sum of the forces z equals 0. I get 0.866 PC plus 0.7071 TD minus 300 equals 0. So using 2 and 3, you can find TC and TD, and then substitute those back into the first equation and get TB. And what I find is TB is 139 pounds, TC is 203 pounds, and TD is 176 pounds. And next time, we'll start talking about calculating moments.